Today's problem is path in directed graph. This problem is on InterviewBit, so you can pause the video, go over to InterviewBit, try it out, come back and we'll walk through the solution. Difficulty easy? It depends. I mean, it's about as easy as you can get for a graph question. So let's see, this is asked in, I'm not sure what that is, hang on. Okay, this is asked at Uber. Problem description, given a directed graph, directed graph, meaning that the edges between the nodes are one way. So if you've got node 1, node 2, and a directed edge from 1 to 2, then you can traverse from 1 to 2. You cannot traverse from 2 to 1. Undirected graph, an edge goes both ways. You can go either direction on the nodes. But what we got here is a directed graph having A nodes, A is one of the inputs, labeled from 1 to A, containing M edges given by matrix B of size M by 2, such that there is an edge directed from node B I0 to node B I1. So B is a list of two-element lists where each two-element list describes a directed edge from index 0 to index 1. Find whether a path exists from node 1 to node A. Return 1 if the path exists, otherwise return 0. There are no self-loops in the graph, meaning a graph that has an edge to itself. There are no multiple edges between two nodes. Okay, I assume that means, well, let me look at the example here. I'm not actually sure what it means. Multiple edges between two nodes. I'm going to assume that that means that there are not like two edges from 1 to 2. Now, I don't see that it would be a problem if there was an edge from 1 to 2 and an edge from 2 to 1. The graph may or may not be connected. Nodes are numbered from 1 to A. Your solution will run on multiple test cases. If you are using global variables, make sure to clear them. I'm not using global variables, using class variables, but that's fine. Problem constraints. A, number of nodes is between 2 and 10 to the 5th, 100,000. M is between, this number of edges, 1 and minimum of 200,000 or the number of nodes. Okay, that's interesting. The number of nodes. So the thing about the multiple edges, I mean, okay, so we can have 100,000. Oh, okay, so there's not going to be 200,000. There's not going to be 200,000 nodes. Because we would have to take the the maximum that this can be, A at A minus 1, is 100,000. So, okay, maximum number of edges, 100,000. And the vertices, it's saying here, it's just saying that the vertices will be valid. Okay, input format. First argument is an integer A, number of nodes. Second argument is B. B is the edges. Return 1 if a path exists. Otherwise, return 0. All right? Examples. Well, okay. Um, you could spend some time looking at this. I've actually already looked at it. There is no path from 1 to 5. Now you can see that right away. A is 5, so the question is there a path from 1 to 5? And there is no inbound edge going to 5, so no, there's no path. I mean, we're going to have to figure it out a different way, but now this one is going to work. We can go from 1 to 2, 2 to 3, 3 to 4, 4 to 5, done. So first one is a 0, second output is 1, and all right, let's take a look at this. I've put a class in here called Digraph, Directed Graph. You don't have to do that. You don't have to do that. I like to do it because for me it's easier to think about it with a graph class. And if you're doing this in an interview and you're interviewing for a position where you're going to be doing object-oriented programming, it's an opportunity to demonstrate your ability to create and use custom objects. All right. Now, it's not a complicated class. There is one, I mean, what we're using it for really is B comes in as a list of edges. So like this in input 1, like this. It's not usable in that format. All right. I mean, we're going to do a depth first search here. So we're going to start at 1, and then we're going to see, well, what nodes, if any, are adjacent to node 1. And if we find one, then we're going to say, all right, well, in fact, we could find one right here, 2. What nodes are adjacent to node 2? But the thing is, in order to find what nodes are adjacent to, say, node 1, you're going to have to search the whole list. You have to go through the whole list because there's one here, and there's also one here. So you could say, well, all right, we can go from 1 to 2. Now, where can we get from 2? Well, now you have to search the list for 2. And here's 2, and 2 goes to 4, and you got to search the rest of the list and see if anything else is an edge from 2. It isn't. So now you got to search the list for the 4. 4 goes back to the 1. All right, that's a problem. So anyway, you need to get this into what's called an adjacency list. An adjacency list is a format for representing graphs that is actually usable. All right, and we'll come back and talk more about adjacency lists. But let's see how this starts out. So we have the input here. We're going to create a graph, okay, a directed graph. The input to the directed graph is the number of nodes. Now, A is the number of nodes, sort of, but the nodes are numbered from 1 to A. So A being 5 and Java being a zero-based, Java using zero-based indexing, we actually have to add 1 to that and say, all right, we're going to make A equal to 6, and that way we'll have an index of 5. Right? That's because that's what we care about. So let's look at the constructor here for the graph. Now here is our adjacency list of lists. Okay, we pass in the number of nodes. We instantiate the adjacency list, and then for each index from 0 to v minus 1, we add an array list to the adjacency list. So what we have here is, at this point, after we run the constructor, a list of empty lists. And in the example that we have here, they would be going from 0 to 5. Okay? Create the graph. Now, for the edges, go through all the edges in B, and we have an add edge method in the graph. Add edge, index 0, index 1. What does add edge do? Add edge gets the list at index V, that's the source node, and adds W. That is the node that the directed edge goes to. Okay. So once we've gotten through this loop here, we've got our adjacency list. Now, as I said, you don't have to create this graph class. You do have to create the adjacency list. Now, if you want to create the adjacency list, somewhere up here in the solution class, you can do that. But you have to have the adjacency list. All right, marked. This is for depth first search. In depth first search, you always have to have a way to know which nodes have you already visited, and in this case, we are using a Boolean array called marked. Initially, everything will default to false here in marked. We call depth first search with the graph and source vertex 1. All right, we come in here, the vertex, we will set the vertex to marked, and for every vertex that is adjacent to the source vertex. So we can call the ADJ method on Digraph with the source vertex. What does ADJ do? ADJ just returns ADJ.getV. So it returns the list at index V, and that's all the nodes that are adjacent to V. All right. Let's see. Okay, mark B. Okay, so we've got all the adjacent nodes, and we look at it. Is it marked? Have we visited already? And if we haven't visited it already, then we do a depth first search on that node. Okay? At the end of this, all the nodes that we were able to reach will be marked. So we will return, because we don't return Boolean here, they want us to return 1 or 0. If node A is marked, that means we reached it. And so we return 1. If we didn't reach it, we return 0. Is there anything that I overlooked here? No, I think that's it. Okay. So this is a basic graph traversal, depth first search. Something that comes up a lot is that in these kind of problems, it seems to be customary to give you edges in the form of a list of 2-element lists. And as I said, like this. And as I said, that's not usable. You need to convert those to adjacency lists. If you want to do that with another class, you would have a constructor, an add edge method, and an ADJ method to get the adjacency list of a particular vertex. It's up to you. but you have to get the adjacency list. All right, let's try running this. Okay, that's pretty fast. All right, so that's it. If you found this helpful in your understanding of graphs and graph traversals, hit like, subscribe, check out the playlist on the screen. Keep leveling up your interview skills. If this problem felt familiar, that is because it follows a pattern, and that is a graph traversal, a depth-first search. I've put together a free guide covering the patterns that show up the most often in interviews, and that includes graph traversals, depth-first search. The link to that is in the video description, and we will see you next time.